Welcome to Physics 150 Podcast, Chapter 11, Sections 1 through 6. At the end of this podcast, you should have a better understanding of waves and energy transport, transverse and longitudinal waves, the speed of a transverse wave on a string, what periodic waves are, a mathematical description for these periodic waves, and graphing waves. So let's get started for today. So, waves and energy transport. A wave is one of the basic models used by physicists. So what are waves? Well, I think everybody's probably seen water waves. And then what else do waves do? Well, waves is some sort of disturbance that travels away from its source. That's what a definition of a wave is. And mechanical waves would be like water waves, sound waves, or seismic waves. So I'm making sound waves with my voice. They're traveling away from my voice box to the microphone and being picked up by the microphone. Waves transmit energy from one point to another without transporting any matter between the 2 points. That's the most important thing about a wave is it can transmit energy without transmitting any matter between 2 points. Now, the way we measure waves, we use a term called intensity, represented with a capital I, and it is measured by the average power per unit area. Or if we wanted to calculate it, we would take the power P and divide it by the area, and that would give us the intensity in which the waves are traveling through. And the units are watts per square meter. Alright, so there's two types of waves. I have a video here of a transverse wave. And as you notice, the red is a string, and you notice that the medium, the string, is moving in the opposite or perpendicular to the motion of the pulse going down the string. So you see here that as the wave moved, you see here that the string was moving up and down, not left or right, as the wave traversed through. And that's the definition of a transverse wave. The medium moves perpendicular to the propagation of the wave. Now, the other type of wave is a longitudinal wave. And in this wave, the medium moves parallel to the direction of propagation. And that's easily seen in a spring. And as I play this video, you will see this area. You see this area where the spring is compressed more and it is traveling down to the other end, and you can actually see one come back. This is in slow motion. There it comes back, and we'll get one more pulse there going down again. See how it's closer together in the pulse and farther apart when the pulse isn't there. That means that the spring is moving left and right, closer together, farther apart as the pulse goes down the spring. Alright, so we're going to talk about how waves, how do we calculate the speed of a wave on a string. And right here, I'm going to show you a video of 3 strings. There's red, yellow, and green. And these strings are all set up with the same tension in the string, the same force in the string are equal, but the mass per unit lengths are different. And what I want you to do is tell me which string's wave or pulse is moving faster, and which one is moving the slowest, and which one is moving the fastest. So here we go. So you can definitely see that the green string's pulse is definitely moving faster than any of the other pulses. The red string's pulse is moving the slowest. So what happens here is and the red string has the largest mass per unit length, while the green string has the smallest mass per unit length. And so what this tells us is the speed is inversely proportional to the mass per unit length of the string. And we're going to use that to help us to figure out what the velocity of a wave would be on a string. Now, I've changed the situation here. The mass per unit length of all the strings are the same, and what's different is the force or the tension in each string. The red string has the largest tension, and then the yellow string is half of the tension of the red, and the green string is half the tension of the yellow. And what I want you to do here is the same thing. Which pulse is traveling the fastest and which pulse is traveling the slowest? I think by looking at this for a few seconds, you can easily determine that the red string was moving the fastest and the green string was moving the slowest pulse. And so this tells us that that the tension in the string is directly proportional to the speed of the wave, while the mass per unit length is inversely proportional to the mass per unit length. So this allows us to come up with this expression. The velocity of any wave on a string should be equal to the square root of the tension in the string divided by mu. And what is mu? Well, v is the velocity, t is the tension, mu is the symbol we use for mass per unit length. Okay? And we calculate that by taking the total mass of the string and dividing it by its total length, and that gives us the mass per unit length. Alright, how do we use this information in a problem? So I'm going to do problem 7 here. We have a transverse wave on 5 stretched strings with the following properties. Rank the strings according to the time it takes a transverse wave pulse to travel from one end to the other end and then all the way back. That's what I worked this problem, from one end to the other end and all the way back. So if we do that, how do we solve that? I think I've worked this a little more difficult than it needs to be. Alright, so for part A, we got the velocity of the string here. Okay. The square root of tension over mu. Let's put the information in what we have. Our tension is F. Our mu would be mass per unit length, mass divided by the total length of the string. And we get this expression for the velocity for part A. Well, I need to figure out how much time it's going to take to travel down and back. And what I'm going to do is the velocity should be equal to its distance traveled by the time divided by the time it takes to travel that distance for the pulse. Well, the distance I chose for its string to travel is 2L. And what they wanted is the time. So what we need to do is solve this expression for the time. And if I do that, I get this expression. I want to simplify this a little bit. I don't like the fraction in the bottom, so I'm going to rearrange it so the fraction is on the top. I don't like the 2L being outside the square root, and if I put it inside the square root, I have to square the 2 and square the L. So that leaves me with this expression for delta t. Well, you notice I have an L squared on top and an L squared on bottom. An L squared on top and an L on the bottom. One will cancel, and I'm left with this final expression of the square root of 4 times L times m divided by the force F. So that would tell us the time it takes for it to travel from one end of the string down to the other end and back. So I do the same thing for B, except for B I have a different force, I have a different parameters to deal with. My force is twice as large as the force in A. And so if I, not my force, my length is twice as large as it in. The force and mass are the same, so that leaves the distance I travel is 4L in this case compared to the first problem. So if I do all the same math and I solve for delta t, I get this expression. You notice how this is larger than A, so this takes more time than A. Now I do the same thing for C, but in C the difference is the mass is twice as large as it was in both A and B. And then I solve for the velocity for part C, and when I do that, I get this expression. Notice that's exactly equal to the same time I had for part B. And then I do this again for part D. In this case, the force was twice as large. I solve for my velocity, my time, for part D, and I get this expression. I do it again for E, putting in all the things I know for the speed of E, and I find out that my time should be this. So once we've done the math, that problem asks us to arrange from largest to smallest, and you definitely see E is the largest time there. So the correct answer for this should be E. Both B and C have equal time. A would be next, and D would be the slowest. Now we're going to talk about periodic waves. What is a periodic wave? Periodic waves represent the same pattern over and over, kind of like simple harmonic motion. It's repeated over and over and over again. Each repeating section is transporting the energy that was used to generate it. That's the definition of a periodic wave. Here's a graph of a periodic wave, and we can use this to describe some quantities of it. What are periodic waves? Music notes are periodic wave. What are not periodic waves? Noise is not a periodic wave. So what properties do periodic waves have? Well, they have something called a crest, and that's usually the maximum part of the wave. They have things called troughs, and that's the lowest part of the wave. They also have something called a period, and that's the time for it to travel one complete cycle. There's something called the frequency, and that frequency equals to 1 over the period, just like we've talked about before. And they also have something called a wavelength, and the definition of the wavelength is exactly the same. It is the distance it takes to travel one complete cycle. So here it's the distance between troughed and troughed. And the last thing would be the amplitude, and the amplitude is basically max displacement from its equilibrium position. And there's more periodic waves. A type of periodic wave is called a harmonic wave, and we can describe that using sines and cosines. It's called sinusoidal disturbance. If we have a sinusoidal disturbance or a harmonic wave, we can predict the maximum speed of a point on the string, or how fast it's going up and down, its max speed going up and down, because it mimics simple harmonic motion. And that would be equivalent to its angular frequency times its amplitude, just like simple harmonic motion. I can also predict its maximum acceleration of a point on the string. And that's, again, just like simple harmonic motion. It is the angular frequency squared times the amplitude. Now, you can calculate the intensity of these waves because the intensity is proportional to their amplitude. So it gives us a way of relating or coming up with a ratio problem if you need to figure out the intensity of the wave, and you don't know the area it's passing through or its power. You want to also be able to calculate the speed of a wave, and the speed of any wave is always equal to its velocity, or its velocity is always equal to the wave's wavelength times its frequency. We're going to need to describe these waves mathematically. To do that, I have to use a function that has two variables in it, and our variables will be position and time. This function will describe the displacement of the medium in which the wave is traveling. So if it's a string, it would describe how far the string is above or below its equilibrium position. And if they're harmonic waves, I can use sines and cosines to describe them. So I have graphs here of two harmonic waves. I can either use sines or cosines. You see the angular frequency here times t minus a new thing called k times the position x for the cosine wave. The sine wave has an addition there instead. Well, what is this k? By definition, k is called the wave number, and we determine the wave number by taking 2 pi and dividing into 2 pi the wavelength. And that tells us the number of wavelengths we can get into 2 pi. How do we determine which direction these waves will travel? It's easy. We look at the signs associated with the omega t and the kx terms of the wave. If the signs are opposite, it moves in the positive x direction. If the signs are negative, it moves in the negative x direction, or the left. The positive x direction would be the right. We need to represent some sort of graph for these waves. The way we're going to do that is we're going to take our function that we just described, and I'm going to freeze it in time. The way I'm going to freeze it in time, or I'm going to freeze it in one variable. Let's choose position first. So I'm going to look at the medium that it's at the location of x equals 0. I'm only going to look what's happening to that one particle and see what happens to it over time. That changes the function we would be looking at would be similar to this. So, and I can graph that function, and that function looks like that. Well, what does this graph tell me? Well, it tells me where this one particle at x equals 0 would be located as t changes. So you can see it starts out at 0 at t equals 0, and then goes to max amplitude about 0.3 seconds, goes back to 0 about a half a second, and then to its maximum negative amplitude at about 0.7 seconds, and then back to 0 again at about 1 second later. And so it tells us exactly what's happening at this one point as it's going up and down. Now, I can do the same thing, but I can freeze freeze t. I'm looking at the entire string now at t equals 0. I'm looking at every position on the string at t equals 0. So it's like taking a picture at t equals 0 and what the string would be located at that point. And if I do that, I get this particular representation. And you notice it looks kind of similar, but not exactly similar. So again, what does this tell us? Well, I know at the point on the string of say a half a meter down the way that string is not moving at t equals 0. That point is not moving at t equals 0. I know at about 3/4 of a meter or a quarter of a meter that point of the string is I know that has to be at its max amplitude. How do we use this information we've just learned to help us solve some problems? Well, we'll look at problem 74 here. The speed of the wave on a lake depends on the frequency of the wave. For waves of frequency 1 hertz, the wave speed is 1.56 meters per second. For 2 hertz waves, it's 0.78 meters per second. The 2 hertz waves from a speedboat's wake reach us 120 seconds after the 1 kilohertz waves generated by the same boat. How far away is the boat? That's what they want us to do, figure out, is how far away is the boat. So if I draw a picture, I have our boat and I have us, or you, they're separated some distance. Let's call that distance delta x. Now what else do I know? Well, I know T1 is the time for the 1 hertz wave to travel the distance delta x. I'll make T2 the time for the 2 hertz wave to travel a distance x. Well, I know the relationship between those two. I know that it takes, after the 1 kilohertz wave reaches me, that's time T1, it takes another 120 seconds for the time T2 to reach me. So I know that these two times are related. I also know the velocity of the 2 kilohertz wave, or say the 2 hertz wave, should be equal to its change in position divided by its change in time. And I put in the change in time associated with T1. I know the velocity of the 1 hertz wave. It's its change in position divided by the time it takes to travel. The whole idea is we want to find delta x. I have no idea what T1 is. So what I want to do is solve one of the equations for T1 and plug it in the other. I'm going to solve the velocity for the Alright, so if I solve this for T1, I get this representation for T1, and I'm going to plug it back in to my equation for the velocity of the 2 hertz wave. So if I do that, I get this representation for V2. Now I can solve that for delta x. That's what I'm looking for. So to do that, I cross multiply. I multiply out by V2. And then I'm going to group terms on one side of the equation that have delta x in it. If I do that, I get this expression. I can now factor out a delta x. And now I can solve for delta x. So what do you get when you put the numbers in? I put my numbers in because I know my velocities. I get that we are 187.2 meters away. Alright, more practice. Let's deal with this harmonic wave right here. Can we answer the questions for this harmonic wave? If we know that the angular frequency is 600 and the wave number is 6. Alright, what is the amplitude of the wave? That's quite easy. That is just 4 millimeters. What is the wavelength? By definition of the wave number, we know that k has to be equal to 2 pi divided by lambda. So if I solve this for, I know that number has to be 6. So if I solve this for lambda, I get this. And my wavelength comes out to be 1.05 meters. What is the period of the wave? Well, one of the definitions for period is that it's 2 pi divided by omega. My omega is 600. So I get 0.0105 seconds for my period. Part D is what is the speed of the wave? And by definition, the speed of the wave should be its wavelength times its frequency. I have its wavelength, I don't have its frequency, but I know the frequency is equal to 1 over the period, and I do have the period. So I take these two numbers and divide one into the other. I get 100 meters per second. This wave is moving. What is the direction of the wave? To find the direction of the wave, I need to look at the signs of both omega t and kx parts of the wave. They are opposite, so it has to travel in the plus x direction. All right, so you should have a better understanding of all the things that we discussed earlier. Uh, See you next time. Bye.